Galileo would not have tried to answer it in his dialogues concerning the two great systems of the world. One of the characters, Simplicio, refers to that manifest cause which everyone knows is gravity. To this Salviati replies, "You should say that everyone knows it is called gravity. I do not question you about the name." He continues, "But about the essence of the thing." And that, he concludes, is precisely what cannot be defined. A physicist like Huygens, who expects the explanation of natural effects to be expressed in the familiar mechanical terms of bodily impact, has other objections. "I am not at all pleased," he writes to Leibniz about Newton, "with any theories which he builds on his principles of attraction, which seem to me absurd. What shocks Huygens is a scandal that Newton himself cannot avoid facing. It is the scandal of action at a distance, of the force of gravity being propagated instantaneously across great distances and producing effects at some remote place, but no effects along the way." Newton recognizes the strangeness of such a force. In a letter to Bentley, he echoes Huygens's protest to Leibniz that gravity should be innate, inherent, and essential to matter, he says, so that one body may act on another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. The absurdity of action at a distance seems to be recognized by common sense and philosophy alike. No action of an agent, Aquinas remarks, however powerful it may be, acts at a distance except through a medium. And Kant, who regards Newtonian physics as the model of a rational science of nature, speaks of a force of attraction without contact as a chimerical fancy which we have no right to assume. How can Newton avoid this absurdity without violating his rule of method in mathematical physics, not to frame hypotheses? Newton's dilemma can perhaps be stated in the following alternatives. Either the inverse square law of gravitational attraction is to be treated as a purely mathematical and hence a purely descriptive proposition of great simplicity and generality, or it must be given physical meaning by a causal explanation of how gravitational force operates. On the first alternative, Newton can avoid framing hypotheses, but the physical meaning of the concepts he employs to state the mathematical law is then left dark. On the second alternative, he can solve the mechanical problem created by such words in his law as attracts and force, but only by going beyond mathematical physics into the realm of mechanical hypotheses. Newton seems to take the first alternative in his mathematical principles of natural philosophy, and the second in his optics. There he proposes the hypothesis of an ethereal medium to explain the attractive force of gravity. Is not this medium, he asks, much rarer within the dense bodies of the sun, stars, planets, and comets, and in the empty celestial spaces between them? And in passing from them to great distances, doth it not grow denser and denser perpetually, and thereby cause the gravity of those great bodies towards one another, and of their parts towards the bodies? Every body endeavoring to go from the denser parts of the medium towards the rare. And though this increase of density may at great distances be exceeding slow, yet if the elastic force of this medium be exceeding great, it may suffice to impel bodies from the denser parts of the medium towards the rarer with all that power which we call gravity. The hypothesis fits the law of gravitation if, as Maxwell points out, the diminution of pressure in the ether is inversely as the distance from the dense body. Newton recognized, according to Maxwell, that it then becomes necessary to account for this inequality of pressure in this medium. And as he was not able to do this, he left the explanation of the cause of gravity as a problem for succeeding ages. The progress made towards the solution of the problem since the time of Newton, Maxwell adds, has been almost imperceptible. The problem of the mechanical properties of an ethereal medium occurs in another form, in the field of optics. Here it is complicated by the rivalry between two theories of light: Newton's corpuscular theory and Huygens's undulatory or wave theory. Each involves a mechanical hypothesis, one engineering the motion, one concerning the motion of particles emitted from the light source, and one concerning the wave-like propagation of the light impulse through a medium. Both theories involve the motion of particles in their explanation of the ore which appears bent in the water. Both appeal to the action of the particles in the refracting medium on the light corpuscles, or the light waves. Both theories, furthermore, are expressed by their authors in a mathematical form which permits the deduction of quantitative facts, like the equality of the angles of incidence and of reflection. The bending of the light ray in refraction, according to the law of sines and the recently discovered fact of the finite velocity of light, Huygens' book gives prominence to the explanation of the strange phenomena of double refraction found in a certain kind of crystal brought from Iceland spar. But both theories seem to be equally competent in dealing with the established facts of reflection and refraction, and the new facts about dispersion. For a century, at least, their rivalry resembles that between the Ptolemaic and Copernican theories, at a time when they seemed equally tenable so far as accounting for the phenomena was concerned. Later, new discoveries, such as those by Young and Fresnel, tend to favor the wave theory of light, but the rivalry continues right down to the present day. It remains unresolved, at least to an extent which prompts Eddington, in reviewing contemporary controversy about the nature of light and electricity, to suggest the invention of the word wavicle to signify the complementary use of both particles and waves in the modern theory of radiation. Unlike the rivalry between the Ptolemaic and Copernican systems, which seemed for a while to be entirely a matter of different mathematical descriptions of the same phenomena, the conflict between these two theories of light involves from the very beginning an issue between diverse mechanical hypotheses to explain the phenomena. That issue is argued not only with respect to the adequacy of either theory to explain such phenomena as the rectilinear propagation of light and its different behavior in different mediums, but it is also debated in terms of the underlying mechanical conceptions. As a gravitational force acting at a distance raises a mechanical problem, which Newton's ether, as the medium through which light is propagated in waves, raises mechanical problems which, if insoluble as they seem to be, contribute even more heavily to the general scientific scandal of mechanics. The two authors take different attitudes toward hypotheses and mechanical explanation. Huygens has, as we have seen, begins his book with the express intention to investigate the causes and to express them in terms of mechanical motions. Newton, on the other hand, begins his with a reiteration of his disavowal of hypotheses. My design in this book, he writes, is not to explain the properties of light by hypotheses, but to propose and prove them by reason and experiments. Nevertheless, Newton's explanation of how the prism produces from white light the band of colors in the spectrum seems to require the assumption of a distinct kind of light corpuscle for each color. And in addition, the assumption that although all light particles have the same velocity when they travel together, making white light, separate particles for different colors are differently refrangable, that is, differently susceptible to the action of the particles in the refracting medium of the glass. Perhaps only in Newton's somewhat artificially restricted sense of the word hypothesis could these assumptions escape that denomination. In any case, the existence of Huygens' rival theory prevented his escaping a controversy about hypotheses. In the queries attached to his optics, he engages in that controversy with an acumen which shows another side of his genius. Huygens' wave theory requires what anybody would have to call an hypothesis, and requires it from the very start. It is inconceivable, he writes, to doubt that light consists in the motion of some sort of matter. He immediately rejects the notion that light rays consist in the transport of matter coming to us from the luminous object in the way in which a shot or an arrow traverses the air. Traverse the air. If for no other reason because the rays traverse one another without hindrance. The similarity between the phenomena of light and the phenomena of sound suggests to him the way that light spreads and causes him to extend the mechanics of sound conceived as a wave motion to light. We know that by means of air, which is an invisible and impalpable body, Huygens argues, sound spreads around the spot where it has been produced by a movement which is passed on successively from one part of air to another, and that the spreading of this movement taking place equally on all sides ought to form spherical surfaces, ever enlarging, and which strike our ears. Now, there is no doubt at all that light also comes from the luminous body to our eyes by some movement impressed on the matter which is between the two. If, in addition, light takes time for its passage, it will follow that this movement, impressed on the intervening matter, is successive, and consequently it spreads as sound does by spherical surfaces and waves. For I call them waves, from their resemblance to those which are seen to be formed in water when a stone is thrown into it. Huygens is aware, however, that the analogy between light and sound is far from perfect. If one examines, he says, what this matter may be in which the movement coming from the luminous body is propagated, one will see that it is not the same that serves for the propagation of sound. This may be proved, he goes on, by shutting up a sounding body in a glass vessel from which the air is withdrawn. An alarm clock beating its bell in a jar without air makes no sound, but a jar with alarm clock beating its bell in a jar without sound makes no sound. Without air makes no sound, but a jar without air is no less transparent than one with air. Since when the air is removed from the vessel, the light does not cease to traverse it as before, and since waves have to be waves of something, and light waves cannot be waves of air, they must be waves of a substance, says Huygens, which I call ethereal matter. This ether, a transparent medium permeating the whole universe, proves to be what Einstein calls the enfant terrible, terrible, in the family of hypothetical physical substances, postulated by Huygens in order to explain light mechanically. It in turn calls for a mechanical account of its own extraordinary properties. Huygens does not avoid this new problem, but neither does he undertake to solve it completely. Suppose one takes a number of spheres of actual size made of some very hard substance and arranges them in a straight line so that they touch one another. Then, says Huygens, one finds, on striking with a similar sphere against the first of the spheres, that the motion passes as in an instant to the last of them, which separates itself from the row, without one being able to perceive that the others have been stirred. This type of motion in the ether would account for the extreme velocity of light, and yet the progression of motion is not instantaneous, as the motion of light also is not. Now, in applying this kind of movement to that which produces light, Huygens continues, there is nothing to hinder us from estimating the particles of the ether to be of a substance as nearly approaching to perfect hardness and possessing a springiness as prompt as we choose. Beyond this, Huygens does not go. It is not necessary to examine here, he says, the causes of this hardness or of that springiness, though we shall ignore the true cause of springiness, we will see that there are many bodies which possess this property, and thus there is nothing strange in supposing that it exists also in little invisible bodies like the particles of the ether. But difficulties which Huygens did not foresee make his ether more than a strange supposition, almost a mechanical impossibility. Huygens had thought that light waves are transmitted in the ether in the way that sound waves are in the air, that is, longitudinally, the direction in which the individual particles vibrate being the same as the direction of the wave motion itself. But when in the 19th century it was found that the phenomena of the polarization of light could not be explained by the corpuscular theory, but only by the wave theory, thus shifting the scales decisively in favor of the latter. It was also found that the wave theory could explain polarization only on the assumption that the motion of the ether particles which produce the light waves is not longitudinal, but transverse, that is, in a direction perpendicular to the waves produced by the vibration of the particles. As Fresnel pointed out at the time, the supposition that the vibrations were transverse was contrary to the received ideas on the nature of the vibration of elastic fluids. They had all involved, as in the case of air as the medium for sound, a longitudinal transmission. The character of the ether is changed by the requirement that its particles vibrate transversely. It ceases to be an air-like ether and must be imagined as a jelly-like ether. The task which Huygens had postponed, that of giving a mechanical explanation of the ether, he had posited in order to state the mechanics of light, becomes in consequence far more difficult, if not impossible. In their efforts to construct the ether as a jelly-like mechanical substance, physicists, according to Einstein, had to make so many highly artificial and unnatural assumptions that they finally decided to abandon the whole program of mechanical explanation. Of Newton's two objections to the wave theory of light, the second, by itself, seems to create an insuperable difficulty for Huygens' ether, even before the realization that it must be a jelly-like medium. Newton's first objection is that any wave theory is inconsistent with the fact of the rectilinear propagation of light. If light consisted in precession or motion propagated either in an instant or in time, it would bend into the shadow, for, he points out, pression or motion cannot be propagated in a fluid in right lines beyond an obstacle which stops part of the motion, but will bend and spread every way into the quiescent medium which lies beyond the obstacle. The waves, pulses, or vibrations of the air wherein sound consists bend manifestly, even though not so much as the waves of water. This objection loses its force when in the 19th century light's bending is experimentally discovered. But Newton's other objection gains force when, 2 centuries after he made it, a jelly-like density is imposed upon the ether by the experimental facts of polarization. This second objection does not point to the inadequacy of the wave theory with respect to the phenomena which must be described, but rather calls attention to its inconsistency with celestial mechanics. Light travels through interstellar space, but so also do the planets. Newton's astronomy accounts for the motion of the planets with great precision, only on the supposition of no resistance from a medium. To make way for the regular and lasting motions of the planets and comets, he writes, it is necessary to empty the heavens of all matter, except perhaps such an exceedingly rare ethereal medium as we described above. Here he refers to the ether he himself had posited as a possible cause of gravitational attraction. Its resistance, he thinks, is so small as to be inconsiderable. The planets and comets and all gross bodies can perform their motions more freely in this ethereal medium than in any fluid, which fills all space adequately without leaving any pores. Such a dense fluid serves only to disturb and retard the motions of those great bodies and make the frame of nature languish. Since it hinders the operations of nature, and since there is no evidence for its existence, Newton concludes that it ought to be rejected. The next conclusion follows immediately. If it be rejected, the hypotheses that light consists in pression or motion promulgated through such a medium are rejected with it. Newton would seem entitled to draw these conclusions because no matter how slight the density of ethereal matter, the use of the ether in the wave theory of light involves some interaction between the particles of ether and the particles of matter. Unless such interaction takes place, no explanation can be given of the change in the velocity of light when it enters a medium like glass or water. Since in Newton's universe there is no difference between terrestrial and celestial matter, Newton cannot accept as ether, which interacts with the matter of glass or water, but does not interact with the matter of the planets. This objection of Newton's, pointing to an inconsistency between the kind of ether required by the wave theory of light and the unretarded motion of the heavenly bodies, appears not to have been answered, but only waived at the time of the wave theory's ascendancy. The famous Michelson-Morley experiment on ether drift later reopens Newton's penetrating query about the ether. But this occurs at a time when physicists are prepared to give up not only the ether, but also with it the mechanical explanation of gravity and light, which it had brought into conflict with one another. Before the mechanical dogma runs its course, it has a career in other fields of physical inquiry. The phenomena of heat, magnetism, and electricity are explored and explained under its inspiration. The history of these subjects is marked by a very rash of hypotheses. Each time mechanical explanation is attempted for a new domain of phenomena, new substances are added. The postulated entities, calorific, magnetical, and electric fluids, are unobservable and without weight. In Newton's terms, they are occult, though it must be added they are no more occult than the ether Newton himself postulated to explain gravity, or the ether Huygens postulated to explain light. In fact, each of these new substances seems to resemble the aeriform or fluid ether, just as each is conceived as the gravitational or optical ether was earlier conceived, in the context of the issue of action at a distance as opposed to action by contact. They would seem to be unobservable in a mechanical account of the traditions of heat, magnetism, and electricity. The phenomena of heat, Lavoisier writes, are difficult to comprehend without admitting them as the effects of a real and material substance or very subtle fluid. Wherefore, he continues, we have distinguished the cause of heat, or that exquisitely elastic fluid which produces it, by the term of caloric. Lavoisier declares himself unable to determine whether light be a modification of caloric, or if caloric be, on the contrary, a modification of light. But in terms of observed effects, he does not attribute ether-like properties to caloric. This subtle matter, he says, penetrates through the pores of all known substances, for there are no vessels through which it cannot escape. The theory of caloric serves its purpose before it gives way to the theory of heat as molecular motion, a conception which can be integrated with the molecular or kinetic theory of gases. This development of the kinetic theory of matter, writes Einstein, is one of the greatest achievements directly influenced by the mechanical view. It is all the more striking, therefore, that in the opening pages of Fourier's Analytical Theory of Heat, wherein he reviews the triumphs of explanation achieved by Newton and his successors, Fourier should so flatly assert, but whatever may be the range of mechanical theories, they do not apply to the effects of heat. These make up a special order of phenomena which cannot be explained by the principles of motion and equilibrium. It is equally striking that Lavoisier seems to have anticipated not only the mechanical theory of heat, but the possibility of a purely mathematical treatment of the phenomena. We are not obliged to suppose caloric to be a real substance, he writes. It is sufficient that it be considered as the repulsive cause, whatever that may be, which separates the particles of matter from each other, so that we are still at liberty to investigate its effects in an abstract and mathematical manner. The second of these two things is precisely what Fourier proposes to undertake, but he disavows any interest in the first, namely the explanation of heat in terms of the mechanical separation of particles by repulsion. In language which resembles Newton's disavowal of concern with the cause of attraction, Fourier declares that primary causes are unknown to us, but are subject to simple and constant laws, which may be discovered by observation. In another place he writes of the nature of heat. Only uncertain hypotheses could be formed, but the knowledge of the mathematical laws to which its effects are subject is independent of all hypothesis. Fourier's aim, therefore, with respect to the very extensive class of phenomena not produced by mechanical forces, but resulting simply from the presence and accumulation of heat, is to reduce the physical question of problems of pure analysis and to express the most general conditions of the propagation of heat in differential equations. He expresses his indebtedness to Descartes for the analytical equations which that mathematician was the first to introduce into the study of curves and surfaces, but which are not restricted to the properties of figures and those properties which are the object of rational mechanics. These equations, he insists, extend to all general phenomena, and from this point of view, mathematical analysis is as extensive as nature itself. This strongly worded statement affirms the mathematical character of nature as the support and justification for a purely mathematical physics. If Fourier remarks about causes and hypotheses, Fourier's remarks about causes and hypotheses are reminiscent of Newton in his mathematical mood. How much more is Fourier's faith in pure mathematical analysis reminiscent of Galileo? Like Galileo, and unlike Newton, Fourier never deviates from his indifference to causes and never softens his judgment of the incompetence and irrelevance of mechanics to the subject he is investigating. His trust in mathematical analysis, which is able by itself to yield and organize physical discoveries, not only revives the spirit of Galileo, but also seems to have inspired Clerk Maxwell to turn from a mechanical to a mathematical theory of electricity. Certain of Fourier's mathematical achievements, such as his theory of dimensions, prove useful to Maxwell. More important, perhaps, is the fact that Maxwell's predictions about the propagation of electromagnetic waves, later experimentally verified by Hertz, are the result of mathematical analysis. With such a demonstration of the power of mathematics to work fruitfully with experiment and without any aid from mechanical hypotheses, Maxwell gives up the attempt to formulate a mechanics for his equations describing the electromagnetic field. He is quite content to let his field theory state the mathematical structure of the phenomena. Between Fourier and Maxwell comes Faraday, one of the greatest experimenters in the whole tradition of science. Faraday discovers this phenomena, whose mathematical structure Maxwell later develops. He prepares the way for Maxwell's application to electricity and magnetism of the method Fourier had practiced. His speculations concerning the relation of electrical and gravitational force point ahead beyond Maxwell to the possibility of a field theory which might unify all physical phenomena under a single set of mathematical laws. Faraday sees no incompatibility between experimentation and speculation. On the contrary, he says that, as an experimentalist, I feel bound to let experiment guide me into any train of thought which it may justify, being satisfied that experiment, like analysis must lead to strict truth if rightly interpreted, and believing also that it is in its nature far more suggestive of new trains of thought and new conditions of natural power. Faraday's faith seems to have been amply justified. His experiments not only discovered a stunning number of new facts, but the speculations to which they led transformed the whole mode of thinking about electricity and magnetism, and to some extent, the whole of physics. The Elizabethan Gilbert, which his bold and brilliantly handled thesis that the Earth is a magnet had made magnetism appear something more than a random phenomenon, occasionally met with in nature. But not until Faraday's discoveries of diamagnetism, announced in a memoir on the magnetic condition of all matter, would anyone have dared to say that all matter appears to be subject to the magnetic force as universally as it is to the gravitating? The electric and chemical or cohesive forces of electricity he can only predict as the result of his protracted experimental investigations, that it is probable that every effect depending upon the powers of inorganic matter will ultimately be found subordinate to it. These remarks indicate the controlling theme of Faraday's researches, namely the convertibility and unity of natural forces. It seems to have been suggested to him by the discovery that both electrical and magnetic forces obey the same simple inverse square law as the force of gravitational attraction. The fact that certain forces obey the same law, or that their action can be described by the same equations, would not of itself reveal whether one of these forces is primarily or all are derivative from some other primary force. But it would suggest questions to be asked by experiment. Gilbert compares magnetism and electricity, but he is not able to convert one into the other. Oersted, before Faraday, is the first to establish one aspect of their convertibility. He shows that an electric current has a magnetic effect. Faraday succeeds in showing the reverse, that a magnetic current has electrical power. He expresses his fascination with such reversibilities in his remarks on the electrical torpedo fish. Seebeck, he writes, taught us how to commute heat into electricity. And Peltier has more lately given us the strict converse of this, and shown us how to convert electricity into heat. Oersted showed how we were to convert electric into magnetic forces, and I had the delight of adding the other member of the full relation by reacting back again and converting magnetic into electric forces. So perhaps, in these organs, where nature has provided the apparatus by means of which the fish can exert and convert nervous into electric force, we may be able, possessing in that point of view a power far beyond that of the fish itself, to reconvert the electric into the nervous force. Faraday demonstrates still another such reversibility in nature. The nature of his discovery is indicated by the titles on the papers in which he announces it. On the magnetization of light and the illumination of magnetic lines of force, and the action of electric currents on light. These papers, in his opinion, establish for the first time a true direct relation and dependence between light and the magnetic and electric forces. And he concludes them with an explicit statement of the central theme of all his researches and speculations. Thus, a great addition is made, he writes, to the facts and considerations which tend to prove that all natural forces are tied together and have a common origin. It is no doubt difficult, in the present state of our knowledge, to express our expectation in exact terms. And though I have said that another of the powers of nature is, in these experiments, directly related to the rest, I ought perhaps rather to say that another form of the great power is distinctly and directly related to the other forms. One form of the great power remained to be connected with such other forms as those of light, heat, electricity, and magnetism. That was the power of gravitational force. Faraday comes to this last stage of his speculations concerning the unity of nature's powers in terms of his conception of lines of force, and of what later came to be called the field of force. The earliest theories of electricity and magnetism, in an orthodox atomistic vein, have conceived them as exerting an influence by means of the effluvia which they emitted. Newton, for example, speculates on how the effluvia of a magnet can be so rare and subtle as to pass through a plate of glass without any resistance or diminution of their force, and yet so potent as to turn magnetic needles beyond the glass. When electrical conduction is later discovered, effluvia are replaced by fluids, on the analogy of caloric as the fluid conductor of heat. But when Faraday finds that he can induce from one current to another, he becomes interested in the dielectric, non-conducting medium around the circuits. He is strongly averse to any theory which involves action at a distance, and so he argues that induction takes place by the action of contiguous particles. To support that argument, he shows experimentally that electrical induction can turn a corner. From his study of all the phenomena of magnetism, Faraday forms the conception of lines of force, and concludes that there is a center of power surrounded by lines of force which are physical lines, essential both to the existence of force within the magnet and to its conveyance to and exertion upon magnetic bodies at a distance. He says of this idea of lines of force that all the points which are experimentally established with regard to magnetic action, i.e., all that is not hypothetical, appear to be well and truly represented by it. And he adds, whatever idea we employ to represent the power ought ultimately to include electric forces, for the two are so related that one expression ought to serve for both. Subsequently, Faraday satisfies himself as to the physical reality of electrical lines of force, in addition to the magnetic lines. The compulsion of his interest in the unity of nature then drives him to speculate about gravitational force. He begins by admitting that in the case of gravitation, no effect sustaining the idea of an independent or physical line of force is presented to us. As far as we at present know, the line of gravitation is merely an ideal line representing the direction in which the power is exerted. But encouraged, perhaps, by Newton's repeated references to the attractions of gravity, magnetism, and electricity, and by Newton's letter to Bentley, which he interprets as showing Newton to be an unhesitating believer in physical lines of gravitating force, Faraday goes to work experimentally. The report of these researches on the possible relation of gravity to electricity opens with the restatement of Faraday's central theme, the long and constant persuasion that all the forces of nature are mutually dependent, having one origin, or rather being different manifestations of one fundamental power, has made me often think of establishing by experiment a connection between gravity and electricity, and so introducing the former into the group, the chain of which, including also magnetism, chemical force, and heat, binds so many and such varied exhibitions of force together by common relations. His experiments, he tells us, unfortunately, produced only negative results. But that does not shake his strong feeling of the existence of a relation between gravity and electricity. Though Faraday fails to prove that such a relation exists, he does bequeath, as a legacy to 20th century physics, the problem of a field theory which would embrace both gravitational and electrical forces. But whereas Faraday conceives the problem mechanically, in terms of the physical reality as well as unity of all lines of force in which contiguous particles act on one another, those who inherit the problem from him cease to concern themselves with the physical existence of lines of force and their mechanical basis in the action and reaction of bodies, influenced by the amazing generality implicit in Maxwell's field equations. They proceed to search for a purely mathematical statement of nature's structure. In the judgment of the 20th century physicist, mathematics may at last succeed in doing precisely what mechanics, from Newton to Faraday, kept promising but forever failing to do. If the unity of nature can be expressed in a single set of laws, they will be, according to Einstein, laws of a type radically different from the laws of mechanics, taking the form of Maxwell's equations, a form which appears in all other equations of modern physics. They will be, he writes, laws representing the structure of the field. In saying that Maxwell's equations are structure laws, and that they provide a new pattern for the laws of nature, Einstein means to emphasize their non-mechanical character. In Maxwell's theory, he writes, there are no material actors, whereas Newton's gravitational laws connect the motion of a body here and now with the action of a body at the same time in the far distance. Maxwell's equations connect events which happen now and here with events which will happen a little later in the immediate vicinity. Like the equations which describe the changes of the electromagnetic field, our new gravitational laws are, according to Einstein, also structure laws describing the changes of the gravitational field. The heart of the difference between a structure law and a mechanical law seems to be contained in Einstein's statement that all space is the scene of those laws, and not, as for mechanical laws, only points in which matter or changes are present. This contrast between matter and space brings to mind the difference between physics and geometry. Yet Einstein's repeated reference to changes in these space structures also reminds us that the electrical and gravitational fields are not purely geometrical, but physical as well. The structure laws of the new physics may be geometrical in form, but if they are to have any physical meaning, can they entirely avoid some coloring by the mechanical conceptions which have been traditionally associated with the consideration of matter and motion? At least one contemporary physicist appears to think that mechanics survives to bury its undertakers. After describing the development in which geometry progressively swallowed up the whole of mechanics, Eddington observes that mechanics is becoming geometry. In becoming geometry remains nonetheless mechanics. The partition between mechanics and geometry, he continues, has broken down, and the nature of each of them has diffused through the whole, so that, besides the geometrization of mechanics, there has been a mechanization of geometry. According to this view, it is not mechanics, but classical mechanics which the new physics has abandoned. The character of mechanics seems to have altered with the character of mathematical formulations. Field theory, dealing with contiguous areas and successive events, avoids the problem of action at a distance, and also apparently that problem's classical solution in terms of the action of contiguous particles. But another sort of mechanics may be implicit in the field equations which connect events in one area with events in the immediate vicinity. If those equations had been available to him, Newton might have expressed his theory of a variably dense ether, analogous to the modern conception of a variably filled or variably curved space, in terms of structure laws describing the gravitational field. We are left with a number of questions. Is the story of mechanics the story of its rise and decline, or the story of its changing role? Now dominant, now subordinate, now more manifest, now more concealed, at all stages in the development of a physics which is committed to being both mathematical and experimental? Do the status and character of mechanical conceptions change with changes in the form of the mathematical laws which describe the phenomena? Can physics be totally devoid of mechanical insight and yet perform experiments which somehow require the scientist to act on bodies and to make them act on one another? Could a pure mathematical physics have yielded productive applications in mechanical engineering without the intermediation of mechanical notions of cause and effect? Whichever way these questions are answered, we face alternatives that seem to be equally unsatisfactory. Either experimental physics is purely mathematical and proclaims its disinterest in as well as its ignorance of causes, or physics cannot be experimental and mathematical without also being mechanical, and without being involved in a search for causes which are never found. To the layman, there is something mysterious about all this. He stands in awe of the physicist's practical mastery of matter and its motions, which he naively supposes to depend upon a scientific knowledge of the causes, while all the time the scientists protest that the causes remain unknown to an experimental and mathematical physics. Mechanical explanations may be offered from time to time, but the various forces they appeal to can be understood only from their effects, and are nothing more than verbal shorthand for the formulae or equations which express the mathematical laws. Yet they remain cause names and seem to stimulate advances in science, both experimental and mathematical, almost as a consequence of the exasperating elusiveness of these hidden causes. Certain philosophers hold a view which suggests that the clue to the mystery may lie in the word hidden. Causes exist, and we can control them to build machines and explode bombs, but we cannot, with our senses, catch them in the very act of causing, or perceive the inwardness of their operation. If the fact that they are thus unobservable means that they are occult, then all causes are occult, not least of all the mechanical type of cause, which consists in the impact of one body upon another. In the century in which physicists tried to avoid the scandal of forces acting at a distance by postulating mechanical mediums through which one body acted directly on another, philosophers like Locke and Hume expressed their doubts that such causal action is any less occult than Newton had said Aristotle's causes were. The passing of motion out of one body into another, Locke thinks, is as obscure and unconceivable as how our minds move or stop our bodies by thought. The increase of motion by impulse, which is observed or believed sometimes to happen, is yet harder to understand. We have by daily experience clear evidence of motion produced both by impulse and by thought, but the manner how hardly comes within our comprehension. We are equally at a loss in both. In Locke's judgment, we will always remain ignorant of the several powers, efficacies, and ways of operation whereby the effects which we daily see are produced. If scientific knowledge is knowledge of causes, then, how far soever human industry may advance, useful and experimental philosophy and physical things, scientifical will still be out of our reach. When we try to observe efficient causes at work, what do we see? Hume answers that we only see one thing happening after another. The impulse of one billiard ball is attended with motion in the second. This is the whole that appears to the outward senses, nor can we form any inward impression of what takes place at the moment of impact. We are ignorant, he writes, of the manner in which bodies operate on each other, and we shall always remain so, for their force or energy is entirely incomprehensible. As the chapter on cause indicates, Aristotle holds an opposite view of the matter. What takes place in efficient causation may be imperceptible, but it is not incomprehensible. All causes may be occult so far as the senses are concerned, but they are not obscure to the intellect. But Aristotle would also insist that the action of efficient causes cannot be understood if they are totally isolated from other causes. Material, formal, final. A purely mechanical physics, in his opinion, defeats itself by its basic philosophical tenets, which exclude all properties that are not quantitative and all causes except the efficient. Only a different metaphysics, one which conveys physical substances in terms of matter and form or potentiality and actuality, can yield a physics which is able to deal with causes and explain the phenomena. But such an Aristotelian physics from the modern point of view, stands condemned on other grounds. It is not experimental. It is not productive or useful applications. It is not mathematical, nor is it capable of comprehending all the phenomena of nature under a few simple universal laws.